Hello and welcome to the third of our streaming sessions for Monday the 7th of October. We're back again with the free CCNA CyberOps instructor training brought to you by the Open University Cisco Academy Support Centre and the Institute of Coding. Hello Irene. Hiya Dave, how the devil are you, sir? Hi Gareth. Hi Kieran. Hi Carl, hi Tim. Hi Yuriko. Hi Ed. Oh. Oh, it's a long old Monday night, I tell you. And it's going to get even longer. This is a really big chapter. Okay, I'm going to do a little caveat right from the start here. The previous chapters that we've looked at on the free CCNA CyberOps have been relatively small chapters. This is enormous. This is one of the two big networking chapters, and it's covering a huge number of topics. Effectively, we're covering probably about 4 or 5 CCNA chapters all in one here. So, with the best will in the world, there is absolutely no way I can cover everything that is in Chapter 4. So you do need to make sure that you log on, look at the online curriculum in detail and have a good read through Chapter 4, because we could be here until 10 o'clock and we still won't cover everything that's in Chapter 4. I'll just try to cover as much as I possibly can, okay, in the time that is available. Hello to everybody. Hi Carl. Hi Ruth. And what we'll do is we'll get started without further ado, as they say. Okay, so networks. There are many different types of networks, sizes, shapes, flavors, etc. We have the small home office network, generally consisting of a PC or a couple of PCs, possibly a printer, a multifunction device that functions as a wireless access point, router, switch and firewall. We have the SOHO, which is not just an area of London, but it is also the SOHO network, the small office home office network. We have medium to large networks, and then of course we have worldwide networks, of which the internet is quite often termed the most complicated and potentially the most expensive thing that's ever been built by humankind, although I'm not entirely sure about that. I would say the road transport networks have probably run that for a good second, at least. So we get networks of all different shapes and sizes, and there are also different types of networks. However, we normally boil down to either peer-to-peer networks, which is where a workstation basically functions as a client and a server together. All of the workstations effectively have the same overall control on the network, or client-server communications, which is the topic of this particular slide, where we have a powerful system which is functioning as a server, and the server's job is to sit on the network and to listen for requests from clients, and then when they get requests from clients, to actually serve those requests. So a server will quite literally sit on a network and it will listen on a specific IP address and TCP or UDP port number for requests from clients. We can have things like, for instance, file servers, FTP. FTP is a file transfer protocol. We can have a file server which contains storage for many files, and then a file client, FTP client, like for instance FileZilla, would request those files. We can actually put the files up to the server or pull them off of the server. So in the case of a file client and server communications, the server stores corporate or user files, and the client device accesses these files through client software. We have of course a web client server, where we have a web server, quite often in the form of the open source Apache 2 or Nginx web servers, or possibly Microsoft's IIS server. The web server hosts web pages in HTML code and CSS and various other formats, and the web client in the form of a browser Firefox, Chrome, Internet Explorer, etc., would then request those pages. The code is sent across from the server to the client, and then the client, the browser, rebuilds that code into a web page. And we have email client-server communications. This is where we actually have an email server which contains effectively mailboxes, and the email client will either send mail up to those mailboxes or pull mail down from those mailboxes. And of course the email servers communicate with each other as well to send mail from server to server. So client-server communications is a very important form of communication on a network. If we have a look at the diagram here, what we've got is we've got Tier 1, Tier 2, Tier 3 networks. A Tier 1 network is an IP network that can reach pretty much every other network on the internet via what's known as settlement-free peering. In other words, Tier 1 networks can exchange traffic with other Tier 1 networks without having to pay any fees for the exchange of traffic in either direction. These are the big boys. A Tier 2 network is a network that peers for free with some networks, but it still has to purchase IP transit or pay for peering to reach some other portions of the internet. And a Tier 3 network, much smaller now, is a network that solely purchases transit and peering from other networks in order to participate in the internet. So these are your general purpose ISPs, for instance, which would connect internet users to the main internet itself. So the Tier 1s and the Tier 2s, they will normally connect via what's known as an Internet Exchange Point or an IXP, whereas larger networks would connect to the Tier 2 networks via what's known as a POP or a Point of Presence. And it's the Tier 3s that connect back down to homes and businesses. So there's a hierarchy there. I mean, the Tier 1s, wow, it's amazing when you think about it. They just allow the other Tier 1s to allow the traffic to flow through, no cost either direction, either way. The Tier 1s never charge each other. There's sort of a kind of like a gentleman's agreement almost between them. It's quite remarkable. So what we can do is we can actually trace the path. So a cybersecurity analyst must be able to determine the origin of traffic that enters the network and also the destination of traffic when it leaves it. So understanding the path that the network traffic travels along is essential to this. And there are many tools that we can use for doing this. In fact, there is a lab. There's quite a nice little lab where we make use of the CyberOps workstation VM, and we basically trace a route to a remote server using traceroute. We can do something similar, of course, if you're familiar with Packet Tracer. Let's just bring up a Packet Tracer network. Whoops, sorry. Let's just bring up a Packet Tracer network. I hit the wrong F key there. It was going to happen sooner or later, wasn't it? There we go. So you should now see a reasonably complex Packet Tracer network that I built up when I was doing something else completely. If you were looking at the previous presentation, we've got access layer switches, distribution layer switches, core layer up here. And what we can do is we can trace from this PC over here in VLAN 60. So if I hover over that PC, you'll see it has an IP address of 192.168.60.1. We can trace across to the PC that's hanging off of the network over here on 192.168.100.254. Actually, sorry, that was the gateway. 192.168.100.1. Okay, so let's see if we can do that. There you go. You can see I've already had a little go at this. It's always a good idea to test these things. Okay, so we're going to do a tracer to 192.168.100.1. And you can actually see the steps that the packet takes on its way from the source to the destination. It goes to its default gateway. In this case, the default gateway is 192.168.60.253. The actual default gateway is 254, but we're using a protocol known as HSRP here, where we're actually sharing the default gateway between these two distribution layer switches. So if one of them fails, the other one takes over. I'll run that again. It's quite quick. It's quite interesting to watch. So it goes to a default gateway first, which is the active switch, and then it jumps across various routers until it finally reaches the destination. So effectively from this PC up to a default gateway, up to this router, up to this router, across to this router, across to this router, and then finally down to the default gateway. You could probably count them. Let's see if we can count them. So first hop, default gateway, so that's 1, 2, 3, 4, 5, 6 is the destination. 1, 2, 3, 4, 5, 6 is the destination. So you can actually see that we can actually trace a path the packet takes through a network. On a Windows machine, you have to use tracert. This is because Windows was somewhat restricted by the old DOS, disk operating system, requirement that commands had 8 characters and a 3-letter extension. On a Linux machine it would be traceroute. On a Cisco router it would be traceroute. Okay, if I do an ARP -A, you can see something interesting here for the Cisco people out there. Though my default gateway is actually this address here, this is the virtual IP address that's been shared by those two switches. It's HSRP virtual IP address. In my ARP cache I also have the standby router, or standby switch in this case, because they're layer 3 switches, and the active is up there. It's interesting, that, isn't it? Sorry, that was a little diversion for the Cisco people. Okay, so there's lots and lots of labs in this chapter, and it's very, very worthwhile to do those labs. So please try to find the time, if you can, to do those labs. Okay, so communication protocols. And what are protocols? Well, of course, a protocol is just basically a set of rules. So communication protocols are the rules for communications. So our network protocols, they provide a means for the computers to communicate on a network. And providing all of the computers understand those protocols and use the same set of protocols, the communication should go perfectly well. So network protocols dictate, for instance, the message encoding, how we actually get the message in the form of zeros and ones onto the wire or onto the fiber optic cable. Formatting of the message, you know, how the headers are set up, what the fields are like in the headers, the actual size and the size of the protocol data unit. The encapsulation, for instance, how what are known as protocol data units are encapsulated as they move their way down the protocol stack. We'll be looking at the protocol stack in a little while. The size of the message. Messages actually have a minimum and a maximum size dependent on the transmission media that they're going across, the timing, the delivery options. There are many, many things that the protocols determine. We have what are known as network protocol suites. And the network protocol suite is a series of protocols that work together with each other. And these describe the precise requirements and interactions. They effectively define a common format or set of rules for exchanging messages between devices on a network. We've got some common networking protocols on the slide there. For instance, HTTP, Hypertext Transfer Protocol. Its job to transfer hypertext. What is hypertext? Well, HTML code and things like that. So this is a protocol that transfers HTML code and other types of web code from a web server to a web client or a browser. We've got the Transmission Control Protocol, TCP, and the Internet Protocol, IP. The Transmission Control Protocol basically makes sure that we have reliable delivery of data between two devices on the network, whereas the IP protocol really concerns itself with the addressing, how we actually address devices on a network, so as we know the source and the destination, whereas TCP makes sure we can reliably send the data from the source to the destination. If we actually have a look at a protocol suite, this is the famous TCP/IP, Transmission Control Protocol, Internet Protocol Suite. And this has standardized the way in which computers communicate. It's an amazing thing when you think about it, that we have computers of all sorts on the internet. We have Windows machines, we have Linux machines, we have Macintoshes, we have Android tablets, and various other types of computers and operating systems. And yet, they can all send messages to each other perfectly well. They can all understand each other's messages on the internet, and that is because the internet speaks the language of TCP/IP, Transmission Control Protocol, Internet Protocol. Okay, so TCP/IP protocols are specific to the application, the transport, the internet, and the network access layers. So TCP/IP protocol suite is generally represented as a 4-layer model. Sometimes you see it as a 5-layer model, but rarely. It's normally a 4-layer model. The TCP/IP protocol suite is implemented on both the sending and the receiving hosts in order to provide end-to-end delivery of messages across a network. And each one of those layers is responsible for doing a specific job. By breaking it down into that layered structure, what it means is it means that we can have manufacturers concentrate on producing standards and protocols for a specific layer without it impacting upon the protocols and standards that are in other layers. So rather than having to design a great big monolithic block, we can now have a situation where, for instance, we can change a protocol at the internet layer without it having an adverse effect on what's going on at the network access layer or at the transport layer. So it allows great protocol development and also inter-vendor interoperability. So different vendors, providing their systems understand IP and they understand TCP and they understand Ethernet, for instance, to the correct standard, then it doesn't matter whether your network card is made by Belkin and it's communicating with a router that's made by Cisco, and it's running on a motherboard made by Gigabyte, and it really doesn't matter as long as everything's functioning to the correct standards and using the correct protocols. We've got a very powerful system which can allow lots of different vendors to produce equipment that will just talk to each other perfectly seamlessly. Another good thing about having a layered model like this is it makes it easier to teach, because we can break down a subject that's very complicated, computer networking, into much simpler layers with their various protocols, which we can address individually. It also makes it easier to troubleshoot a network by having a layered model. We can troubleshoot at layer 3, for instance, by using ICMP, the Internet Control Message Protocol, things like ping and traceroute that we just looked at. So there are many advantages of having a layered model like this. Of course, the TCP/IP protocol suite isn't the only layered model. There is also the 7-layer OSI suite, which is probably even better for teaching because it's more granular with the 7 layers. Although really the way the internet works is a bit more like the 4-layer TCP/IP model. Okay, communication protocols determine things like, for instance, the format, the size, and the timing of messages. So the format, we need to look at encapsulation. This is the process of placing a message format inside another message format. So when we come down from the application layer, that information is encapsulated inside the segments or the datagrams that live at the transport layer. If we use TCP at the transport layer, it's known as a segment. If we use UDP at the transport layer, it's known as a datagram. And these application layer protocols, like for instance HTTP, would be encapsulated inside a TCP segment. HTTP has to be sent reliably, so it goes inside a TCP segment because TCP is a reliable transport protocol. Whereas if we look at, for instance, TFTP, that's Trivial File Transfer Protocol, I'm not sure what happened there. I was looking at the corner of my eye and I just noticed that the Facebook server did a little glitch, so I hope everything's still running okay. You might have seen a little glitch there. Screen just went blank on the Facebook page for just about 1 second just then. I hope it's all back and working okay. If we have a protocol such as TFTP, Trivial File Transfer Protocol, which doesn't need to be sent reliably, then we can actually encapsulate it inside User Datagram Protocol, UDP, which is a very lightweight protocol. Both UDP and TCP would be encapsulated inside IP at the internet layer, where they become a packet, and then that packet could, for instance, be encapsulated inside an Ethernet frame at the network access layer, where it becomes a frame. Okay, so encapsulation is the process of putting a protocol data unit, which is what we know the entities as at the various layers, inside the protocol data unit on the next layer down. Decapsulation, of course, is the exact opposite. So as a packet, as a frame is decapsulated, we remove the frame header and frame trailer, and it becomes a packet. And then we move the layer 3 or packet header, and it becomes either a segment if it's TCP or a datagram if it's UDP. And when we remove the transport layer header, it would then go up to the application layer, where it's just basically known as data. Wow. We're going quite quick here, aren't we? There's a lot to cover. Okay, so the TCP/IP protocol suite is implemented on both the sending and the receiving hosts. So it's the same protocol suite on both sides, regardless of the operating system that's running on the computers, to ensure good end-to-end delivery of the messages across the network. So encapsulation, as we said, process of placing one message format inside another message format as we work our way down the protocol stack. Decapsulation, the reverse process of encapsulation. So as we're working our way back up the protocol stack, we're actually removing the layers. It's like almost like removing the layers of an onion. Size. Now a message has to be broken down into many frames when it's sent. This is because the transmission medium can only handle a certain size of message on that transmission medium at a specific time. Like for instance with Ethernet, frame size would normally be 1518 bytes, which is known as the MTU, or the maximum transmission unit, maximum size of the frame that's normally handled on an Ethernet network. So if we've got data that's bigger than that, it would actually have to be broken down into frames of that size. So the data would come down from the application layer. We get to the transport layer, where it would either go into TCP or UDP. It would become either a segment or a datagram. At that point it would be broken down into these smaller segments. These smaller segments would drop into the internet layer, where they would have a layer 3 header put on with the source and destination IP address and a few other things, where they would become a packet, and then the packet would drop down into the network access layer, where we would get a layer 2 or frame header and frame trailer put on, and these frames would have to be of a certain size. They can't be bigger than a certain size, normally 1518 bytes on an Ethernet segment. Timing. Timing includes the access method, flow control, and response timeout. There are many access methods used on networks. Some depend on whether the network is a contention-based network, where all the devices are contending to get onto the network, or some kind of controlled access network. Ethernet, for instance, is a contention-based network. Back in the old days, when it used to run at what's known as half duplex, which is where we could send in both directions but not at the same time, where we used hubs, it would make use of what's known as carrier sense multiple access collision detection. And that would be the access method. So on a wired Ethernet network, it would be carrier sense multiple access collision detection, whereas on a wireless network, it would be carrier sense multiple access collision avoidance. This is because you can detect a collision on a wire, but you can't detect a collision with radio waves. So on a wireless network, you have to avoid the collision using clear to send and request to send signals. Flow control. Flow control is purely what it sounds like. It's a way of controlling the flow of traffic. So if the sending device is sending traffic far too fast for the receiving device to handle, the receiving device can basically send a signal out and say, whoa, whoa, slow down. Response timeout, again, exactly what you expect it to be. How long do I wait for a response before I time out and think, well, there's nothing coming? Okay, transmission methods. We have three main transmission methods. This is with IP version 4. We have the Unicast, and a Unicast transmission is a one-to-one transmission. A single host to a single host. This is very, very common. We have the Multicast, which is a one-to-many transmission, but not everybody. It's like one to many people in a group, but not everybody. Multicast is very widely used with streaming video and streaming audio. So, for instance, if you're listening to the internet radio, when you tune into an internet radio station, what you're effectively doing is you're picking a multicast address, and the radio station, the internet radio station, is streaming those packets to that multicast address, and anybody with that multicast address will be listening in to that station. So multicast is one to many, and broadcast is one to all. What they mean there is they basically mean one to everybody on that network segment, on that layer 3 network segment. Okay, broadcasts, if you were listening to the CCNA 2 session earlier, broadcasts have to flow through a switch. A switch has to be transparent to broadcasts. It has to allow the broadcast to flow through it. Whereas a router will stop broadcasts, unless you configure it not to, which would be strange, but you can do that. So a router will normally stop broadcasts, whereas a switch will allow broadcasts to flow through it. It has to work that way because a switch needs to be able to allow broadcasts to flow through it for protocols such as DHCP and ARP to work, Dynamic Host Configuration Protocol and Address Resolution Protocol. If it couldn't allow broadcasts to flow through it, those protocols would break. Whereas a router, of course, needs to stop broadcasts, because if routers just basically allowed all the broadcasts to flow through them, they would all flow straight out into the internet and it would be game over. Okay, so if we have a look at the reference models again, these slides do move about a little bit. We're back on the reference models now, and what we've got is on the left hand side we've got the Open System Interconnect, or OSI model. This is a 7-layered model. Very, very good for teaching. Breaks things down in a lovely way, very granular. On the right hand side we have the TCP/IP model, Transmission Control Protocol, Internet Protocol model. 4 layers. What you can see is that there is actually a way in which we can get a 7-layered model to fit with a 4-layered model. And believe it or not, this slide probably could answer 2, 3, maybe 4 questions in the end of chapter, I would imagine, because they love asking questions about these reference models. So what you need to know is OSI is 7 layers, TCP/IP is 4 layers. You need to know the layers and the order they're in. So on the OSI layer model, we've got application, presentation, session, transport, network, data link and physical. There are many, many ways of remembering this, some considerably ruder than others. All people seem to need data processing. It's a very nice, gentle one. So all people seem to need data processing. Slightly dodgier one, but not too far, is from the bottom up. Princess Diana never tried to snog Prince Andrew. Okay, I did actually clean that up ever so slightly. The application, the TCP/IP model's a lot easier. There's only 4 layers, so we've got 8 in: application, transport, internet, network access. Now, another thing you need to remember is how these layers between the two models correlate. So the application layer of the TCP/IP model will correlate with the application, presentation and session layer of the OSI layer model. That's strange. I've not had any problems with this streaming, but it's just done it again. I just had a flicker. I'm hoping that we're back again. Okay, the transport layer correlates directly with the transport layer. That's a nice easy one. They've even got the same name, so transport layer to transport layer. The internet layer correlates with the network layer, And the network access layer correlates with the data link and physical layer. Key thing to know these things. We can also see some of the typical protocols that occur. So for instance, at the network access layer, or the data link and physical layer of the OSI layer model, we have protocols such as point-to-point protocol, frame relay, and Ethernet. The first two are very widely used on wide area networks, well, PPP more so than frame relay these days, whereas Ethernet is extremely widely used on local area networks. At the network layer, we have protocols which are mostly to do with addressing. So we have IPv4 and IPv6. This is the Internet Protocol, and that is to do with addressing devices on a network, and also protocols which are to do with error messages and testing. So we've got Internet Control Message Protocol version 4 and Internet Control Message Protocol version 6. Very familiar to most people because of ping and traceroute. Transport layer, two big protocols. TCP, Transmission Control Protocol, which is reliable. It makes use of acknowledgements. So because when it sends segments out, they have to be acknowledged. It's a reliable protocol. It's also what they call connection oriented. So it makes use of what's known as a three-way handshake. It sends out a SYN for synchronization. That is replied to with an acknowledgement from the other side. The other side sends out its own SYN for synchronization, which is then acknowledged from this side. So we actually get what's called a SYN, SYNAC, ACK, or a three-way handshake. UDP is a very lightweight protocol. There are no acknowledgements. There's no three-way handshake. So it's known as a connection-less, unreliable protocol, whereas TCP is connection-oriented, reliable protocol. However, there are many instances where you might like to use UDP. For instance, voice over IP traffic is normally sent over UDP because in that case we want minimum delay, maximum speed, and we're not really too bothered if there's a few packets dropped. Whereas TCP, things like for instance emails, where we can't drop any packets because it would change the content of the email, are sent using TCP. And up at the application layer, we've got our application layer protocols, for instance Hypertext Transfer Protocol, Domain Name Service, or Domain Name System as it's sometimes put, Dynamic Host Configuration Protocol, File Transfer Protocol. These are application layer protocols. You do need to know your reference models. Okay, so there's three important addresses with these reference models. At the data link layer, layer 2, we have physical addresses. A typical physical address would be the MAC address, the Media Access Control address. This is the address that's burnt into a ROM chip on your network card. It identifies that network interface card uniquely. It's a 48-bit number, so that's 48 ones and zeros, but it's represented in hexadecimal. So it's represented as 12 hexadecimal digits. And that MAC address is unique to that network card. There will be no other network card in the entire world with the same MAC address on. This is very useful if we're trying to trace somebody to a specific computer. Now it is possible to spoof a MAC address, so we can use the operating system to overwrite the MAC address, but it only overwrites it in software. If we reboot the computer and that spoofing system doesn't run again, it will revert back to the original MAC address that was on the network interface card. So a MAC address is a typical example of a physical address. At layer 3, the network layer, we have network host addressing, and this would be your familiar IPv4 and IPv6 addresses. At the transport layer, we've got protocol addressing. So this is where we have a combination of an IP address and a port number. Specifically, the protocol address is the port number. So for instance, TCP port 80 is used by Hypertext Transfer Protocol, whereas TCP port 110 would be used by POP3, Post Office Protocol version 3. This is used for receiving emails. Or possibly TCP port number 25 would be used by SMTP, Simple Mail Transfer Protocol, used for sending emails. Okay, so addressing is used by the client to send requests and other data to the server. The server then uses the client's address to return the requested data to the client that has received it. The protocol address makes sure it gets to the correct application on the system. The network address makes sure it gets to the correct network, and the physical address makes sure it gets to the correct device on that network. Okay, and right down the bottom here at the physical layer, we can see that the bit is short for binary digit, so in other words the zeros and ones, are then encoded onto the transmission media, either as electrical signals or possibly flashes of light on fiber optic, or if we're using wireless, as radio frequency signals carried on an electromagnetic wave. So here we go, is an example of encapsulation, and don't forget, encapsulation is where we're going down the stack. Decapsulation is where we're going back up the stack. And you can see the protocol data units, or the PDUs. The PDU is the name of the entity at that layer of the networking model. So right down at the physical layer, for instance, we have bits. At the data link layer, layer 2, we have frames. At the network layer, layer 3, we have packets, IP packets generally. At the transport layer, it actually says segments there, but normally they will only be called segments if they're TCP. If they're UDP, they're generally termed datagrams. And then above the transport layer, so on the TCP/IP model, that would be the application layer, whereas on the OSI layer model, it would be the application, presentation, and session layers. It's just known as data. So encapsulation, this is the division of data into smaller pieces. Actually, that's incorrect. The division of data into smaller pieces is called segmentation. Okay, so segmentation is the division of data into smaller pieces. Okay. The segmented messages have two primary benefits. Segmentation. So the benefit of that is that the entity, whether it's a segment or a datagram, is now small enough so that when it works its way down the protocol stack and it gets to the data link layer, layer 2, the frame is not too big for the media that it needs to be sent across. And a really important benefit of segmentation is what's known as multiplexing. This means that we can send a segment that's perhaps an email, followed by a segment that is perhaps a bit of a web page, followed by a segment that's perhaps a bit of a game that you're playing on the computer, and we can multiplex or interleave these segments, which allows it to flow across the wire and make it seem as though we're doing multiple things on the network at the same time. If we didn't use segmentation, let's say for instance you were downloading a big file, that download would completely use up the entire bandwidth of your connection to the internet. And before you could listen to an internet radio station, you have to wait until the download had finished. Or before you could send an email, you'd have to wait until the download had finished. By segmenting, we can send a little tiny chunk of email, then a little tiny chunk of internet radio, followed by a little tiny chunk of game. And if we segment them properly and interleave them properly, it appears that we're doing all of those things at the same time on the wire connected to the internet. Yeah, exactly. It's quite deep. Okay, if we have a little look at encapsulation continued, the encapsulation process is reversed at the receiving end when it's known as decapsulation. So the data is then de-encapsulated as it moves up the stack toward the end user application. So as it comes across from the web server, It comes across the wire as zeros and ones, normally in the form of a voltage if it's a copper cable. It goes into the web client. The web client will inspect the Ethernet frame header to check to see if it has the correct MAC address, and if it is the MAC address that's on the network card of the web client, then it knows that that frame is for the web client. It will then remove the frame header, the Ethernet frame header, move up to the packet. It will look at the IP packet. It can look at the IP address inside the IP packet to make sure it is the correct IP address for this system. It will then remove the IP packet header, de-encapsulating all the way. It will then look at the TCP segment header. In the TCP segment header, it will realize that this particular segment has come across using TCP port 80, which would identify it as coming from a web server, meaning that it should go to the web client on the the web client on the web client, in other words to the web browser on the web client, and then it will remove the transport layer header, the TCP header, and inside that will be the data, which will be, say for instance, the HTML code that it will use to build the web page. And all of this is happening hundreds of thousands of times a second as these frames are flowing into your computer system. It's absolutely mind-blowing how much is going on and how powerful the processors are in modern networking devices and computers to make this possible. So here's a scenario. We're sending and receiving a web page. So at the application layer we've got HTTP, at the transport layer we've got TCP, at the network layer we've got IP, and at the data link layer we've got Ethernet. Or if we use the TCP IP stack, it's application, transport, internet, network access layers. So HTTP, this is the application that governs the way the web server and the web client interact. So for instance, we might be using a HTTP GET request in order to get a web page from the web server. TCP, this is our transport protocol. This manages individual conversations. So the TCP will divide the HTTP messages into smaller pieces, known as segments. TCP is also responsible for controlling the size and the rate at which the messages are exchanged. So this is where flow control comes in. And it does many, many other things as well, TCP. IP is responsible for taking the formatted segments from the layer above, TCP, and then encapsulating them into packets, assigning them with an appropriate address, which is an IP address of course, either IP version 4 or IP version 6, and then delivering them to the destination host. The routers make use of the IP address in order to get the packets to the correct network. Once the packets are at the correct network, then it becomes the job of the switch and the Ethernet address, or the layer 2 address, the MAC address, to make sure they get to the right host on that network. So the Ethernet address, this is the network access protocol, which is responsible for taking the packets from IP, the layer above, and formatting them to be transmitted over the media. Okay, at this particular point you could break off with your students and you could introduce them to Wireshark. There's a nice little Wireshark lab that we can do using the virtual machines and the Mininet topology. Moving on, we can have a little look at the Ethernet protocol. The Ethernet protocol works at layer 1 and layer 2, so the physical layer and the data link layer. It's defined by the IEEE, that's the Institute of Electrical and Electronic Engineers, 802.2 standard and 802.3 standard. Here's a little bit of pub trivia for you. The reason that these standards are called 802 is because the original standards were developed by the Institute of Electrical and Electronic Engineers in February 1980. So that was the second month of 1980, in other words 802. Okay, but these standards would potentially be much later than that. Okay, So there are lots of 802 standards. 802.11 for instance covers wireless. The Ethernet protocol, defined by the IEEE 802.2 and 802.3 standards. The Ethernet sublayers, so at the data link layer, it is the only layer in the entire protocol suite which is divided into sublayers. We have two sublayers. We have the logical link control, or LLC, and the media access control. Now they're easy to remember which one's which, because the media access control is the closest to the media. And don't forget, the media sits right at the very bottom here underneath the physical layer. So the media access control is at the bottom, closest to the media, and the logical link control is at the top, closest to the software. 802.2 is for the LLC, and 802.3 covers the MAC and also physical layer standards. Ethernet's responsibilities are data encapsulation, so it encapsulates the packets that come down from the network layer above, and also media access control, how those frames, which is what they're known as once they're encapsulated, are then allowed to access the media. Here is an Ethernet frame. Bear in mind, Ethernet frames have a minimum and a maximum size. You can't have an Ethernet frame of any size you feel like. The minimum Ethernet frame size is 64 bytes. Anything smaller than that is actually known as a runt frame. Yeah, it's not a particularly nice term for a frame, but a runt frame is a frame that is smaller than 64 bytes. The maximum size for an Ethernet frame is 1518 bytes. Anything bigger than that is known as a jumbo frame. Now, many switches can handle jumbo frames, and under certain circumstances frames could be transmitted as jumbo frames on purpose in order to speed up the amount of data that can be transmitted. However, you do need to know minimum is 64, maximum is 1518 bytes. If we look inside the Ethernet frame, there are many things. We've got a little preamble which indicates the start of the frame. Then we have the destination MAC address, that is a 6-byte field, 48 bits. The source MAC address, again a 6-byte field. The ether type, this identifies the payload that is being encapsulated inside the frame. It's normally going to be IP from the network layer above. And then we have the data itself, which would be the IP packet coming down from the network layer above. And right on the end we have a trailer. Again, the data link layer is unusual. It's the only layer with sublayers, and it's also the only layer that has a header and a trailer. And in the trailer we have a frame checksum. And the frame checksum is a cyclic redundancy check. Basically, effectively it's a bit more complicated than this, but it kind of looks at the length of the frame, divides it by 100, and then drops a number in the frame checksum. When the frame gets to the other side, it looks at the length of the frame, divides it by 100, and if the two numbers match, then the frames come across perfectly correctly without any corruption. It is actually slightly more complicated than that, but that's just a simple analogy of how it works. Now the MAC address, or media access control address, is a 48-bit binary number expressed as 12 hexadecimal digits. Hexadecimal, of course, has 16 digits. 16 digits can be represented by 4 binary bits, so we can compress a binary address by 4 if we convert it to hexadecimal. This is how we go from a 48-bit number to a 12-bit number to a 12-digit number. So because each hexadecimal digit can represent 4 binary bits, we can compress a 48-bit binary address into just 12 hexadecimal digits. Hexadecimal uses the numbers from 0 to 9, and then it starts to use the letters from A to F, because we have to have a single digit. We run out of digits when we get to 9, so we have to start using letters. A is 10, F is 15. All the data that travels on the network is encapsulated in Ethernet frames, on an Ethernet network obviously. If we have a look on the right hand side, you can see MAC addresses in 3 different formats. It is exactly the same address, however it is in 3 completely different formats. If we have a quick look at a MAC address, let's see if we can see a MAC address on here. If I go across to, let's have a little look. I'll pull up one of those Raspberry Pis probably. That might be the easiest way of doing it. Okay, I think we're in the switch there. So let's bring up one of the Raspberry Pis. And if I do an IPL, we can look at layer 2 information with IPL, which stands for IP link. We can actually see the maximum transmission unit here for Ethernet, which it says is 1500. However, that doesn't take into account the header and the trailer. So this is why it's different from the 1518. We can also see the MAC address. And on this particular system, it uses semicolons in between. However, there are different ways of representing MAC addresses, as we could see in this slide. Okay. You need to make sure that your students are very familiar with binary, decimal and hexadecimal and the conversions between them, and they actually understand exactly what is meant by a hexadecimal MAC address. Okay, so IPv4 encapsulation. Encapsulation is on the way down, decapsulation is on the way back up again. We have our PDUs, or protocol data units. Application presentation and session layer is just known as data. Transport layer, it's a segment if it's TCP, it's a datagram if it's UDP. The network layer, it becomes a packet. The data link layer, it becomes a frame. At the physical layer, it's just known as bits. So we can see on the right hand side here that the network layer PDU, the IP packet, has been encapsulated into the transport layer PDU, which is a segment in this case, has been encapsulated into a IP packet, a network layer encapsulation. So as we move down from the transport layer, layer 4, into layer 3, the network layer, this segment has been encapsulated into a packet by putting an IP header on it. Right, believe it or not, we've only got 10 minutes left and we're probably less than halfway through the chapter. So like I say, this is an enormous chapter, there's no way we could cover all of it. You do need to make sure that you have a good read through the chapter. IPv4 characteristics. IPv4 is connectionless. In other words, there is no dedicated end-to-end connection created before data is sent. It's just sent. Best effort. Just send it on its way. It doesn't do what TCP does, where it does that three-way handshake to make sure that the destination is ready before it sends anything. It's completely connectionless IP. It's also unreliable. Best effort delivery. It does not guarantee that all the packets are going to be delivered, or in fact that they're received. So TCP will guarantee this by use of acknowledgements. IP is no acknowledgements. However, IP is media independent. So IP can operate independent of the media that carries the data at the lower layers of the protocol stack. So we can send IP version 4 or IP version 6 over copper cable on an Ethernet. We can send it over fiber optic cable using some form of PPP. It really doesn't make any odds. It's completely media independent. If we have a look at an IP version 4 packet header, there are a lot of things inside the packet header. We've got the version, which is basically 4, version 4. We have these differentiated services and differentiated services code point and things like that. These are used for quality of service. This allows us to prioritize and to classify and prioritize traffic as voice, video or data, giving voice the highest priority, video the second highest and data the last. There's a total length field, identification field, there's all kinds of fields in here. One of the most important ones is this TTL field, the time to live. This is an 8-bit number which is decreased by 1 every time it flows through a router. By the time it's flowed through enough routers, that value will decrease down to 0, at which point the next router will drop it. This is designed in order to stop packets circulating around loops on the network forever. There's a protocol field here which determines the protocol that's actually inside this IP packet. Is it TCP, is it UDP, etc. We've got a source IP address, destination IP address. This is IPv4 packet header. Looks very busy, doesn't it? Yeah, there's a lot of things going on in there. The IPv6 packet header is a lot simpler. Okay, there's a nice video demonstration in this chapter, well worth looking at. It looks at sample IPv4 headers in Wireshark. If we look at IPv4 address notation, an IP address is represented in what's known as dotted decimal. So what we do is we take the 32-bit IP address, we break it down into 4 8-bit octets, and then we convert those 8 bits from their binary into their decimal equivalents. If you wish to have a little look at how that's done, I imagine most people who are watching this probably would be fully aware of how you go about doing this, but I have got some little videos that I put up on YouTube that I made many years ago, but they're still relevant, on how to do IP addressing. So there is that IP addressing under the microscope video. All you need to do is go to Remote Training Solutions. So go to YouTube, Remote Training Solutions, no spaces in between it. There's an IP addressing under the microscope video that will explain how IP addressing works if you are actually struggling with it at all. I've also got some slightly more in-depth ones as well. IPv4 subnetting, classful IP addressing. Okay, so this will explain also some more things. Slightly more in depth, that one. Okay, so an IP address is a series of 32 binary digits, ones and zeros. When a host is configured with an IPv4 address, it is entered as a dotted decimal number, so for instance 192.168.10.10, and we can convert that back to binary. Looking at that, we have 192, we have the 128-bit set to 1, the 64-bit set to 1, all the other bits set to 0, and you can do equivalent conversions for the other 3 octets as well. Needless to say, most people who are coming to this course probably will have a Cisco CCNA background, but not everybody. If you're not that familiar with IP addressing, you do need to work on this one. It is critically important. The IPv4 host structure. IPv4 address is a hierarchical address. It's made up of a network portion and a host portion. The network portion has to be identical for all of the devices that reside in the same network. The bits in the host portion have to be unique to identify a specific host within that network. So looking at this diagram, we've got the 192.168.10 network, and this is host 10 on that network. If I had 192.168.10.20, it would be host 20 on the same network, 192.168.10. So they could communicate with each other across the layer 2 switch, no problem. However, if I had a host 192.168.20.10, that would be on a different network, because it would be on the 192.168.20 network, and they could not communicate with each other across a layer 2 switch. We would actually have to use a router in order to connect those networks together. Okay, the subnetting. Subnetting takes a network addressing space and then divides it into smaller spaces called subnets. So we're taking a big network space and we're dividing it into smaller spaces. This is subnetting. The subnet mask and the IP address can be logically ANDed. This is using the logical AND process. Again, that is covered on my Remote Training Solutions YouTube video. It actually leads you through step by step the ANDing process. But basically, the truth table for an AND is that both the inputs have to be 1 for the output to be 1. So if we look at the IP address and the subnet mask, where we have a 1 in the IP address and a 1 in the subnet mask, the result is a 1. Where we have anything else, like a 1 and a 0, or a 0 and a 0, the output will be a 0. And if you do this ANDing, it's quite interesting because it actually will generate the network address. So if you AND an IP address with the subnet mask, it will always generate the network address. And it's the network address that the router is interested in, because the router's job is to get you from the source network to the destination network. Once you get to that network, then the actual IP address will be used to, via the switch, via what's known as ARP, the Address Resolution Protocol, to get you to the correct computer on that network. Okay, so subnetting takes the network space and divides it into smaller spaces called subnets. And on a router, each interface is in a separate network or a separate subnet. And the nice thing with a router is that it will stop broadcasts from crossing from interface to interface. Routers break up broadcast domains, whereas switches are transparent to broadcast domains. Okay, have a little look at this video on host, network and broadcast addressing. That will drive home some of the concepts we've just been talking about. There are 5 classes of addresses: A, B, C, D and E. D is multicast addresses, E is experimental. The A, B's and C's, though, they are routable on the internet apart from what are known as the private IP addresses. Each class has a private IP address range, and that range is not routable on the internet. Big internet backbone routers, if they see any of these addresses, anything that starts with a 10, anything that starts 192.168, or the ones that range between 172.16.00 and 172.31.255.255, these are what are known as the RFC, Request for Comments 1918 private IP address ranges for the class A, B and C addresses. They are not routable on the internet. However, this is very useful because it allows us to use those ranges internally within our organization, and we'll never ever have an overlap. I could use those addresses in my organization. Down the road, Lidl or Aldi or Asda or whoever could use exactly the same address range. My addresses will never overlap with their addresses because they cannot go out across the internet. This was actually developed as a way of conserving IP address ranges. However, it does bring problems as well because there is no direct end-to-end connectivity. We have to make use of something called NAT, Network Address Translation, to convert these private IP addresses into an internet service provider provided public IP address to route on the internet. Okay, we're just about on time now, and we're probably not quite halfway through this chapter. So just having a little look on here to see if there's anything else. IP version 6. IP version 6 uses 128-bit address space. IP version 6 uses hexadecimal, of course. You would not want to write out 128 ones and zeros. By using hexadecimal, we can compress the 128-bit address space by 4, bringing it down to a string of 32 hexadecimal values. And there are many other ways of compressing IP version 6 addresses. We can remove the leading zeros in every hexdet, and we can also compress a string of zeros into a double colon, but we can only do that once in an IP version 6 address. You cannot compress multiple strings of zeros down into a double colon. So if you ever see an IP version 6 address with more than one double colon in it, something's gone seriously wrong, or somebody's having a bit of a joke with you. IP version 6 addresses will use what's known as a prefix as well, so they'll use a /64 generally speaking. They won't use the long-winded way of doing subnet masks. Okay, I think unfortunately we have pretty much run out of time in our allocated segment for tonight. As I said, this is an absolutely enormous chapter. It's probably the biggest chapter in the entire course. There are an awful lot of technologies to cover. So before you do consider taking the end of chapter test, and definitely before you take the final exam, you want to have a really good read through this chapter, and definitely look at the videos. The videos are excellent. The videos will convey a lot of information in a nice, comfortable way, so have a good look at the videos as well. Okay, please try to use Wireshark, and definitely use Wireshark with your students. I found that students learn very, very well once they're introduced to Wireshark, because they can actually see the protocols and the various protocol data units at the different layers. They can see the SYN, SYN-ACK, ACK, three-way handshakes. They can see all of these things that we talk about in the theory in practice. Okay, so what I'm going to do is I'm going to have to sign off here, because otherwise we will be here until 10:30, probably tonight. Join us next week for Chapter 5, which I'm hoping is a slightly smaller chapter than this one. And Chapter 5 is Network Infrastructure. That will be on the 14th of October at same time, same place, 2000 hours UK time. Thank you very much indeed for joining me, and well done for a marathon session for CyberOps, and I will see you in a week's time, and I hope that you can have a little bit of a relax now. Best wishes to everybody. I'll go and have a little nervous breakdown in the corner now.